Good day to everyone. Our team will present about assignment 3, which is on car engine mounting, failure mode and effect analysis. Let's go to the first part.
Assalamualaikum. My name is Abdul Fattah Iqbal Besa. This is introduction of car engine mounting. Engine mounting systems are vital in automotive engineering, connecting the engine to the chassis to manage vibration and noise. Effective mount ensure passenger comfort and stability, especially as modern vehicles become lighter and more powerful. Damaged mount can cause increased engine movement, vibration, and wear on components, impacting performance and safety. The student-based failure analysis identifies key factors related to engine mounting damage.
Good day to Dr. Ford. My name is Yap Chong Ming from BMKM Session 1. Now I will continue the presentation. The slide illustrates the fishbone diagram, also known as an Ishikawa or cause and effect diagram, made by our group to indicate 6 potential failure modes of engine mounting. The fishbone diagram identifies the potential causes of engine mounting failure across 6 main categories, which are methods, environment, people, measurements, materials, and equipment. Firstly, in the methods category, damage during shipping due to poor packaging and handling can compromise the structural integrity of the mounts and expose them to contaminants, leading to early failure. Next, the environment category highlights the risks of corrosions from moisture, road salt, and other factors which can weaken the structure and cause severe engine movements or complete mount failure. Moreover, under the category of people, inadequate training of technicians can result in improper handling, increased vibrations, and potential engine damage. The measurement categories addresses the issues of incorrect measurements, leading to the selection of engine mounts that are the wrong size or shape, causing misalignments, excessive vibrations, noise, increased wear, and premature failure. In the materials category, using rubber that degrades quickly when exposed to heat and oil can lead to faster deteriorations, sudden failure, reduced damping capability, and increased vibration. Lastly, the equipment category points out that using inadequate or worn-out tools during installations can result in improper bolt tightening, loosening, increased noise vibrations, and safety hazards. This diagram illustrates how various factors contribute to engine mounting failures by affecting the mount's structural integrity, alignment, and durability.
Assalamualaikum and very good day. I'm Amar, metric number B0921101164, and I will present about failure mode and analysis table FMEA, that failure mode that we have recorded. First of all, what is failure mode analysis table? Okay. The failure mode analysis table represents the RPN level for each of the failure modes that we have recorded. For the example, it has 3 elements, which is severity, occurrence, detection. Severity is how it affects the component, the user, or the customer. And the occurrence, how it will likelihood will happen, often happen or not. And detection is how we can detect, easy or hard. So from the failure mode that we have recorded, we already assume all these three elements. For the example, on the first column, which is the method shipping, the potential failure mode is damage mount during shipping due to poor packaging or handling. The potential effect of failure mode is exposure to the contaminants such as dirt, oil, and mixture. The severity that we can assume is 7 because it will impact the structure of the component. And the potential causes of this, of course, it is a mishandling of the company. And the occurrence is 3 because it's not often happen in industry, but it has happened, but not often. Then the next is the current process control is proper packaging and handling protocols. The detection we put 2 because we can easily detect. If we not easily detect, we will put normally high of number. And the RPN, we multiply the severity of this and detection, we get 42. We do the action to decrease the RPN. Okay, the responsibility of these failure modes, we put the logistic teams. And the action taken, conduct a training related to the equipment handling. From the action, we can lower the RPN, which is we get 28. This procedure also same on all of the failure modes, which is on the item of environmental, people, and measurement, materials, and also the equipment. But the highest that we can uh, assume is on the environmental, okay, because it will affect the structure of the equipment. Okay, for example, the on the second column, the potential failure mode is a corrosion of metal component due to exposure to the mixture, and from the potential effects, it will structural weakening the mounting, and severity is very high. It exposed to the environment, occurrence is 5 and detection is 6. Why detection is 6? It's very hard to detect because the mounting is on the engine compartment. So we're not aware on this component. But if it fail, then all of the structure of the engine will fail. So it's very critical. Okay. So that is the what can I say, the simple uh, form of this table that we can create. We just assume it based on our level of study. Okay, that's all for the FMEA table. After the FMEA table has represent, now we move to the calculation of risk priority number for each failure mode and how we create the Pareto analysis. Before we do the Pareto analysis, we must do a table that represent the highest RPN into the lowest RPN. The highest that we can record is the corrosion of metal that I already say on the previous slide. The second, improper measurement, technician fault, indicate, worn out tools, premature engine mount wear, use of rubber that degrades quickly, and lastly is damage to mount during shipping. The RPN level is the highest is 240 and the lowest is 42. The total of the RPN is 882. And we do relative numbers, we do the cumulative number of failure modes, and we do the cumulative relative numbers. So based on all of these data, we create one of the simple Pareto analysis. Okay, as you can see on the left side, there is the Pareto analysis that we have created. The y-axis is and the x-axis represent the failure mode. So from the 80%, you can see that there has 4 components or 4 elements that we must focus based on our potential failure mode. But this will present on my team member on the next slide. I think that's all from me. Thank you very much.
From the presented Pareto analysis, faults such as corrosion of metal components, improper measurement, technicians' faults during installations, and inadequate or worn-out tools used for installations occur very often and significantly influence the work of car engine mounting. They make up about 80% of the causes producing an examine effect. Corrosion of metal components is one of the top concerns as it seriously endangers safety and at the same time comes with relatively high occurrence and detectability scores. Solving this problem goes through the prompt usage of modern coatings resistance to corrosion that will be applied to the metal parts. Furthermore, using more powerful and more frequent routine maintenance measures will have an impact on preventing the initiation and spread of corrosion. Inaccurate parameter measurement is another significant issue as well since it has a negative impact on the vehicle's performance and alignments. To reduce and tackle this measurement uncertainty, it is necessary to implement better quality tests during the measuring process and verify that all measurement instruments are correctly calibrated on a regular basis. Moreover, technicians' installation faults also pose a high severity risk. This risk can be greatly reduced by creating training programs that help technicians learn the needed skills and by creating a signification system that guarantees their proficiency in installation procedures. Lastly, the problem of inadequate or worn-out tools can be effectively managed through regular inspections and maintenance of tools. Replacing damaged or worn-out equipment at the right time will not only help to enhance the reliability and safety of the vehicles components but also extend the lifespan of the equipment. The total risk priority number (RPN) may be greatly decreased by taking care of these important problems, which will improve the automobile engine mounting system dependability and safety. Based on the RPN analysis, high RPNs highlight 4 significant risks, which is the first one, corrosion, with a IPN of 240, and continue with measurement error and technician fault, which is 200 and 144 respectively, and lastly inadequate tools with a 120 RPM. Corrosion is the most critical due to its severe impact and detection challenges. All modes are crucial, prompting actions to reduce RPM level. As a conclusion, the failure mode and effects analysis for the Prodor Viva 2012 car engine mounting identifies critical failures modes such as corrosion of metal components, improper measurement leading to incorrect mounting, technician's error during installation, and the use of inadequate or worn-out tools. These issues are prioritized due to their high-risk priority number and require immediate attention to enhance vehicle safety and reliability. Implementing the recommended actions aim to significantly reduce the likelihood of engine mount failures, thereby improving overall vehicle performance. Pareto analysis suggests that addressing the top 20% of these issues can resolve 80% of related problems, ensuring efficient resource allocation. The FMEA processes also provides a structured approach to prioritize and mitigate risks, leading to higher customer satisfaction and reduced maintenance costs. The analysis classified as pass due to a decrease in RPN serve as an educational exercise for students to understand real-world industry application.
That's all from us. Thank you.